Hello, everyone. I'm Elise Roberts, and I would like to welcome you to today's webinar, organized by the Section on Statistics in Defense and National Security. Our guest speaker is Dr. Thomas Mathew, the Presidential Research Professor of Statistics at the University of Maryland, Baltimore County. Dr. Mathew is a Fellow of the American Statistical Association and a Fellow of the Institute of Mathematical Statistics. He has delivered numerous conference presentations, both nationally and internationally, and has published extensively on methodological and applied topics, including bioequivalence testing, exposure data analysis, and mixed and random effects models, just to name a few. He is the co-author of 2 books, Statistical Tests in Mixed Linear Models and Statistical Tolerance Regions, Theory, Applications, and Computation. In this webinar, Dr. Mathew will formally define what are tolerance intervals and regions, explain their computation for some univariate and multivariate populations, and demonstrate their use with real applications. And with that, I will hand it over to Dr. Mathew to get started.
Presentation will be focused on a bunch of applications, and the applications will come from, there will be environmental applications, engineering, as well as clinical applications. Because some of the concepts that I am going to discuss, they were actually motivated by clinical applications. So a few clinical applications will also be included. Okay, let's go. Here is part 1. So I will give you some motivating examples, definitions, different types of tolerance intervals, and their calculation for some univariate normal distributions as well as log normal distributions. So this is part 1. Okay, let us first try to understand what exactly is a tolerance interval. So over the years, I have noticed that not everyone is familiar with a tolerance interval. We all know what is a confidence interval. In fact, a 95% confidence interval is something we all know very well. If you look at a confidence interval or a prediction interval, it has only 1% or one probability associated with them. And that is the confidence level, typically 0.95 or 95%. Often we denote this by 1 minus alpha. And I will be using the same notation. Now, a tolerance interval has 2 percentages associated with it. One of them we will call the content to be denoted by P. And then we also have a confidence level to be denoted by 1 minus alpha. So you need 2 percentages. That is probably the best way to put it. 2 percentages in order to define a tolerance interval. Now, these quantities, the content P and the confidence level, they can take the usual values. They can both be equal to 0.95 or 95%. They could be different. P could be 0.9, 1 minus alpha could be 0.95, and so on. So you have a variety of choices. So the standard choices are listed here, 0.9, 0.95, and 0.99, for example. So 2 percentages. Okay, let us see what these 2 percentages represent using this example here. This is actual data I got online. So this is collected by what is called the NIOSH, the National Institute of Occupational Safety and Health, from a lab. This is for evaluating the air lead levels within this facility. So as we know, lead is toxic. It is a health hazard. So this data consists of 15 observations at various locations within this lab. You will see that some of the numbers are quite small and some of the numbers are very big. And this is typical of what is called the log normal distribution, because it is a distribution that is skewed to the right. If you take the logarithm of the data and if you do a normal probability plot, you will get practically a straight line. So that means the log transformed data follows a normal distribution, and that is the meaning of the log normal distribution. So at the bottom, I have also included the log transformed air lead levels. Okay, now let's see what we want to do with this data. So I'm going to use this data to motivate what is the content P and what is the confidence level 1 minus alpha associated with a tolerance interval. Now, the Occupational Safety and Health Administration, OSHA, they have specified what is called an occupational exposure limit, or OEL, for lead exposure. That is 50 units. The unit is microgram per cubic meter of air. So on the log scale, this 50 is 3.912. So what this means is, if the lead levels are below this limit, it is reasonably safe. Anything above the limit, above the OEL, is a serious health hazard. So here is the question we want to answer. The data we have obtained, those 15 numbers, can we use it to conclude that 90% or more of the air lead levels will be below this limit? So from now on, we are going to talk in terms of the log transformed data. So the limit now is 3.912. So we want to conclude 90% or more of a population is below a certain limit. You notice this 90% is not associated with a random sample. So this is associated with the population. So when you define a tolerance interval, what we call content is a percentage associated with the underlying population, not a sample. Remember the confidence level? The confidence level captures the sampling variability that represents the uncertainty in the sample. The content P represents not an uncertainty in the sample, it represents a percentage associated with the population. In other words, I want an interval that will capture a certain percentage of the population. That is called the content. So it is the percentage of the population that I want to capture within my tolerance interval. An important point to remember is, going back to the data, based on the log transformed data, which follows a normal distribution, if you were to compute a confidence interval for the population mean, you can use the usual student's T, very easy to do. However, it is not enough to know that the average lead level is below the limit. That is not enough. From the perspective of health hazard evaluation, if possible, you want all the lead levels to be below this limit of 3.912. In other words, if the average is small, not enough, because we are talking about something that is a serious health hazard. You want a majority of the lead levels to be below this limit. This is where the tolerance interval comes into the picture. So you are not trying to capture a population parameter. You are trying to capture the population values, a majority of them within an interval. Now remember, this interval will be calculated using a sample. We have a sample consisting of 15 numbers. And hence, there is sampling variability. And that is where the confidence level will come into the picture. Okay, let's take a look at this. So we will denote by X the log transformed air lead levels. And mu and sigma square will denote the mean and variance of the population. So I have listed a confidence interval for the population mean. So this is the sample mean plus minus the T percentile times S over square root of N. S is the sample standard deviation. I have put there an upper confidence limit for the population mean, a lower confidence limit, a two-sided interval. And I have also included a prediction limit, upper prediction limit for the lead level. So what is an upper prediction limit? I am trying to predict what the air lead level will be in a single sample. So that is the prediction limit. So similarly, you can do a lower limit or a two-sided limit for the air lead level if you want to predict something. So all of these they have exactly one coverage probability or one percentage associated with them, namely the 95%, capturing the sampling variability. So all of them are like the sample mean plus or minus some constant times the sample standard deviation. So this is the usual confidence interval and prediction interval. Okay.
Could we go back to the previous slide? There is a question in the chat.
Yeah.
The question is the content is a population quantile?
That is an important question. I will answer that shortly.
Okay.
Okay.
Thank you.
Yeah, I will answer that in maybe 5 or 6 slides within that. All right. Now, the question we are trying to answer is, can I conclude at least 90% of the air lead levels will be below this limit, 3.912, the occupational exposure limit, 3.912. Here is what we are going to do. We will compute what is called an upper tolerance limit. We will see how to compute that. If that upper tolerance limit is below the 3.912, we will conclude at least 90% of the air lead levels is below this limit. So this is how we are going to address this problem. And the upper tolerance limit will have the same form that you saw for a confidence limit and a prediction limit. So here it is. We will take the upper tolerance limit to be of the form, the sample mean plus a constant times the sample standard deviation, where the constant K is referred to as the tolerance factor. This is what we need to compute. Now remember, this quantity x bar plus Ks, this is a random quantity. So I cannot claim that whenever I take a sample and compute x bar plus Ks, 90% of the air lead level will be below this, because there is uncertainty associated with it. So the best I can say is 90% or more of the population lead level will be below this limit with a high probability, let us say 95%. And that is the confidence level. So again, at the bottom of the screen, I'm trying to explain what exactly are these two percentages associated with the tolerance interval. In this case, what we would call an upper tolerance limit. So what is the 90% once again? 90% is the proportion of the population I want to be below my tolerance limit. What is the 95%? Since this limit will be computed using a random sample, that 95% represents a coverage probability or a confidence level. I hope the distinction between these two is clear. And I hope it is also clear why we need to have these two percentages associated with a tolerance interval because of the question we are trying to answer. Okay, so two percentages, 90%, 95%. So there again is the interpretation. 90% represents the percentage of the population that will be below this limit. The 95% represents the probability of meeting this particular requirement. So content P is 0.9, confidence level is 0.95. Okay, now we will look at the computation of K. So I'm not going to go through any theoretical derivations because first of all, we don't have time for that. And secondly, that probably will make many things confusing. Now, at the bottom of the screen, I have given the expression for the factor K. So that x bar plus Ks is the upper tolerance limit. K depends on a few things. It depends on the quantity P, content 0.9. So you need the corresponding percentile of the standard normal, which is 1.28 from the normal table. It will also depend on the percentile of a non-central T distribution, 101 minus alpha percent, with the degrees of freedom n-1 and non-centrality parameter that ZP 1.28 times square root of the sample size. So then K is given by 1 over square root of n times that non-central T percentile. So if you found that a little bit too much or confusing, don't worry about it. This factor K is available. We have extensive tables available for the factor K in case you want to actually use it. In fact, at the end of our book, you will see several pages of tables listing this quantity K for various values of the sample size n, the content P, and the confidence level 1 minus alpha. Okay, going back to our example. In our example, n is 15, content P is 0.9, and let us say the confidence level is 0.95. Then that non-central T percentile happens to be 8.002. So what we call the tolerance factor K is 2.066. So you can simplify at the bottom. There it is. So it simplifies to 7.926. So according to the formula, x bar plus Ks, it simplifies to 7.926, which is way beyond that upper limit of 3.912. So the conclusion is this particular facility is not safe as far as lead exposure is concerned. So we cannot conclude that that requirement that NIOSH wanted, 90% or more below the limit of 3.912, that is not happening here. Okay, let me go back for a minute. So this is the solution to the example and the conclusion we have. Okay, one more thing. So we computed the upper limit to be 7.926. So how do you interpret it? So here is my interpretation. So I will conclude 90% or more of the air lead level will be below 7.926. And I am 95% confident of this statement. Pretty much a similar interpretation we have for the confidence interval as well. Okay. Now, I would like to take the question that was raised a little while ago. Now, for a normal distribution with the mean mu and standard deviation sigma, we know what the percentile is. That will be the mean mu plus the standard normal percentile times sigma. It so happens that the upper tolerance limit is an upper confidence limit for this percentile mu plus Cp sigma. So basically the upper tolerance limit has an interpretation as an upper confidence limit, not for the mean, but for a population percentile. So if P is 0.9, we are actually computing an upper confidence limit for the 90th percentile, namely mu plus 1.28 sigma. Okay, we went through this solution to the example. To do the lower confidence limit, it has the same form. Instead of x bar plus ks, it will be x bar minus ks for the same factor k. You can simplify, and the lower tolerance limit comes out to be 0.740. So in this application, the lower limit is not of much interest because when the air lead level is low, which is good, right? You don't want to put a limit on it. However, I did this just to illustrate the calculation. So what does this 0.740 mean? How do you interpret it? It simply means 90% or more of the air lead level. They will be above 0.740, and I am 95% confident of that. Now, the question that was raised, I hope it got answered. If not, let me know. Now, the lower tolerance limit also has a confidence limit interpretation. It is a lower confidence limit for a percentile, for the 1 minus pth percentile. Now, let me look at a clinical example. So this talks about the creatinine level, which is used to check how well your kidneys are functioning. So if you go to the Mayo Clinic website, you will see the following normal ranges for the creatinine level for men and women. You know, if you go to a physical checkup, the doctor will look at all sorts of lab result, cholesterol or blood sugar and creatinine. That's a possibility. So here they are. So this is what would be called a normal range. So this is a whole area of research. It comes under what is called laboratory medicine. And the computation of this is very, very statistical. I will go through some of this if there is time as we proceed with the webinar. These limits could vary with race, gender, then age, and so on. So this is basically the limits reported on the Mayo Clinic website for adult men and adult women. Okay.
We have a quick question in the chat. Is it not a population quantile, but rather an upper or lower 95% bound on a quantile?
Well, the population quantile is unknown to me, right? The population quantile is unknown. Okay, let me go back for a minute. So look at the bottom. The 90th quantile of the population is mu plus 1.28 sigma, right? That is the 90th quantile. I don't know that because I don't know what the population mean and population standard deviation are. Now, suppose I simply estimate it. That means this will be in the place of mu, I will use the sample mean x bar. In the place of sigma, I will use the sample standard deviation s. That will give me x bar plus 1.28 s. Will that meet my requirement? My requirement is 90% or more of the air-lead level should be below the limit. A point estimate may not satisfy that requirement. An upper tolerance limit will satisfy the requirement with a high probability, namely 0.95. So we are not simply estimating a percentile, because the estimated quantile will not meet the requirement we are asking. But a confidence limit, which is the upper tolerance limit, will meet that requirement with a very high probability, namely 0.95. I hope that clarified it. If not, let me know. We can revisit this again. All right. So I saw a data set in this book. This is a sample of 284 data on the creatinine level for 284 healthy individuals from some population. So the sample mean is 85 and the standard deviation is 14.34. Now we want to compute a range that will include 90% or more of the creatinine levels for the healthy population. That means I now want a lower limit and an upper limit. But this interval will be computed using the sample. So I have to have a confidence level associated with it. In other words, we are now going to compute what would be called a two-sided tolerance interval, which will have a lower limit and an upper limit. Okay. So we will take it to be x bar minus ks to x bar plus ks for a suitably chosen factor k. Now, interestingly, this interval does not have a confidence interval interpretation. So the upper tolerance limit, it was a confidence limit for a certain quantile. The lower tolerance limit was also a confidence limit for a quantile. The two-sided tolerance interval is not. This is not a confidence interval for anything. Okay. So now it is a matter of computing the factor k. There is no closed form expression. There are good approximations. There are also extensive tables available. So I have listed the factor k for a few values of the sample size n and also the content p when the confidence level is 0.95. So here is an approximation for k. This involves, the numerator involves this quantity chi-square 1p 1 over n. This is the pth percentile of a non-central chi-square with non-centrality parameter 1 over n. And the denominator is a percentile of the central chi-square. And this is a table that will list the approximate, which is A, and the exact. You can see that they are both pretty close. I have listed this only for a small sample size. When the sample size becomes large, even for 10, they are actually practically the same. So that approximation is actually very good for practical purposes. For the creatinine example, K is 1.771, and here is the interval. So the interval simplifies to 59.6 to 110.4. A little bit different from what the Mayo Clinic is listing, but remember that this is computed for a different population. So what is the interpretation of this? So the meaning is 90% or more of the individuals in this population will have their creatinine level between 59.6 and 110.4, and I am 95% confident of that. So that is what it means. I have also computed when both the content and the confidence level equal to 0.95, I have again computed the interval here. Okay, let me quickly mention this. In a laboratory medicine, there is the concept of what is called a reference interval. And a reference interval is actually meant to capture the central part of the healthy population. In other words, you want an interval. What is meant by healthy? Central part. Think of the normal distribution. The central 95% means you go from the 2.5th quantile interval that will capture the central part of the distribution. That means an interval that will capture the 2.5th percentile, which is mu minus 1.96 sigma, and the 97.5th percentile, mu plus 1.96 sigma. Such an interval is called a central tolerance interval. Remember, a confidence interval is meant to capture a population parameter like the population mean. A central tolerance interval is meant to capture a population interval, namely mu minus 1.96 sigma to mu plus 1.96 sigma. So this is how the laboratory medicine people define what is called a reference interval or a central tolerance interval. Okay, I have explained the calculation here. There's a quote here. It says the reference interval is the most widely used medical decision-making tool. It is central to the determination of whether or not an individual is healthy. Because if you adjust the interval a little bit, today I am healthy, tomorrow I am not healthy. So it's a very important quantity and it has to be computed subject to the appropriate criteria.
Oh.
Yeah, go ahead.
Oh, could we go back 2 slides to slide 32? And we had a question in the chat. What if you do not want your two-sided tolerance interval centered at the mean?
Well, then the interval will become wider. That's an interesting question. Look at the normal distribution. If you want to capture 95% of the distribution, this is not the only interval, but this is the interval that is centered at the mean. And that will give you the shortest interval.
Okay, thank you. I think that answers the question.
Right. Yeah. Okay. I think I will stop part 1 here. So here's what we have discussed so far. I introduced the tolerance interval concept to you using an examples. Depends on 2 percentages, content and confidence level. And we discussed different types of interval. You can have just an upper limit, lower limit. It could be two-sided. And the last part we discussed was what is called a central tolerance interval. We discussed their computation and illustrated them with examples. Okay. We will now go to part 2. I will briefly mention about the gamma distribution, and then we'll spend some time on non-parametric tolerance limits. Most of the time I will spend in part 2 for the computation of non-parametric tolerance limits. Okay, this example I took from this book on statistical methods for groundwater monitoring. They report data on alkalinity concentrations in groundwater. And what they wanted was to compute an upper tolerance limit for the alkalinity concentration using content 0.9 and confidence level 0.95. So I am just copying the data from the book and also telling you what was the purpose of the data analysis reported in the book. You can verify that the gamma distribution fits the data quite well. It's skewed, right skewed, and the gamma is a good fit. So this is alkalinity concentration in groundwater obtained from the site of a waste disposal landfill. You have a sample of 27 numbers. So here is the gamma density. A is the shape parameter and B is the scale parameter. I don't know if you have seen this. There's a nice normal approximation for the gamma. And that is, if X is gamma, the cube root X to the power 1/3 is approximately normal. It is called the cube root normal approximation. This goes back to, I think, 1930s probably, from a paper due to Wilson and Hilferty. It is also called the Wilson-Hilferty approximation.
Hi, Dr. Mathew.
Yes.
We have a question in the chat. I think it's referring to the previous slide. Were these data collected at the same time from different wells or across multiple time points? Concerning about potential spatial or temporal non-homogeneities.
I understand the question. I think this is collected at the same time from different locations.
Okay, thank you.
Yeah, because if this is collected at different time points, there will be a time, there will be a time series aspect coming into the picture, which I don't think that was the case here.
Okay, thank you for the explanation.
Okay. So this is called a cube root normal approximation. This is highly accurate unless the shape parameter A is very, very small. The scale parameter B does not influence the quality of the approximation. If the shape parameter is, what we have noticed is, if the shape is like less than 0.1, the approximation can be a little bit inaccurate. But if the shape parameter is reasonably big, 0.1 or more, the approximation in our experience is highly accurate. The advantage is once you are in the normal distribution, we have all sorts of nice formulas. You can apply them here. So in order to compute a tolerance interval for the gamma, so here is a simple recipe. I have my data. You take the cube root of the data, then pretend you have sampled from a normal distribution, apply normal distribution formulas, compute the tolerance interval, and in the end, take the third power. So we are done. So very simple. So that is what is mentioned here. I have my sample from the gamma, take the cube root, pretend the cube root, the yi, you have a sample from the normal, compute the tolerance limit, upper, lower, two-sided, whatever you want, based on the normal distribution formulas, which we just discussed earlier. Then in the end, take the third power. So there it is. If you take the cube root, the sample mean based on the cube root data will be y bar right here and the sample standard deviation. And then remember, we have this tolerance factor. You compute it. Compute the tolerance interval, tolerance limit based on the cube root data, that is 4.6051. Take the third power. That will be the upper tolerance limit for the alkalinity concentration. So here the content is 0.9 and the confidence level is 0.95. Minus alpha is 0.95. I remember giving this gamma part, a talk at the EPA some time back, and they were surprised that something this simple is possible with the gamma. So if we look at the usual way of computing a tolerance limit for the gamma distribution, it's pretty messy and it involves approximations and not all that accurate. This is highly accurate unless the shape parameter is very small. By the way, a small shape parameter can come up in some applications. Then this should not be applied. Okay, so this is the comment. Actually, the upper limit is still okay. The lower limit becomes really problematic when the shape parameter is really small. Okay, I have listed there are likelihood-based procedures when you have a very small shape parameter. So I have listed some of the references here. Okay, we will now spend some time on computing non-parametric tolerance limits and tolerance interval. So far we have focused on the normal, the log normal gamma. We have a definite parametric distribution. What happens if that is not the case? Okay, I'm going to introduce this to you using an example. This is some consulting I did, and I got hold of the data. I'll share some of the data with you. This deals with the nuclear power plant safety and the analysis of what is called a loss of coolant accident. Well, in a naive way, this can be explained as if you lose coolant, then the power plant will warm up and there could be an accident. So you want to prevent that. And I have put some quote from the US Nuclear Regulatory Commission site, what exactly is meant by LOCA, loss of coolant accident. So the nuclear reactor, this is a very, I should say that simplistic explanation of what is going on, because I don't know the technical, I have no idea about the technical details. So there is something called cladding, and this is what is protecting, right? Protecting the reactor, what is called a cladding. And if the thing becomes very hot, that means if it exceeds 2200 degrees Fahrenheit, the cladding temperature, the cladding can become kind of like shattered, brittled, and it could become fragmented, and there could be an accident. So the way they verify if the plant is safe is as follows. So what they will do is you obtain data on the peak cladding temperature based on output from computer codes, so that you are actually simulating a nuclear accident. Obviously, you cannot get actual data, right? You cannot get actual data on a nuclear accident. So you simulate the data, and then using the simulated data, you compute a non-parametric upper tolerance limit, having both content and confidence level both equal to 0.95. And if the upper tolerance limit is below the 2200, you conclude that the PCT is mostly below 2200, and we conclude things are probably safe. This is how it is done. Okay. So what we want is a non-parametric upper tolerance limit. Okay. Why is it non-parametric? Okay. Here is some data. This is a sample of size 208. So I got this from this company for whom I did some consulting, and they gave me the data. So this is a few numbers in the data, the PCT values in the sample of size 208. It does not follow a normal distribution. In fact, it looks to be bimodal. If you look at it, here's a histogram. Looks to be bimodal. Probably there's a way to address it assuming a bimodal distribution, but they prefer, this company preferred a non-parametric upper tolerance limit. You can see that there were some values that were actually very close to 2200, or maybe there was one that exceeded 2200. I don't actually remember. Okay, now let us see. So I will go through the computation of non-parametric tolerance limit, then we'll apply it to that example regarding that nuclear power plant safety examples. Okay. Now the calculation of a non-parametric tolerance limit, this will be based on order statistics. And the procedure applies only to continuous distributions. And we use the following standard result. Basically, you are trying to look at the distributions involving order statistics. So this is something we all know. The CDF follows a uniform zero-one distribution when you have a continuous random variable. Second, let's say you have a random sample from a continuous distribution. Order it from the smallest to the largest, and then any order statistic, if you evaluate the CDF at an order statistic, then that quantity has a beta distribution free of any unknown parameters. The joint distribution of two order statistics, once you evaluate them at the CDF, that joint distribution is also parameter free. Remember, the CDF is for the original random variable, the CDF of the underlying distribution. Okay. And then between the binomial and the beta, there's a relation. So you may have seen this. Says the following: if y is binomial, then the probability y is greater than or equal to some quantity is the probability a beta random variable u is less than or equal to p. Okay, so what is the p? P is the probability under the binomial. What is the r? R is involved in the parameters of the beta distribution. So these are properties that are used to compute non-parametric tolerance limits. And they're based on order statistics. The question is, which order statistic? So here is what we will do. So let us start with the computation of an upper tolerance limit. So I want to find R so that the rth order statistic is an upper tolerance limit having content P and confidence level 1 minus alpha. So here is what we will do. You consider a binomial NP distribution. So N is the sample size, P is the content. P is the content. Now, for the binomial, you pick the smallest integer R so that the binomial CDF at R minus 1 is at least 1 minus alpha. So I have a binomial distribution. So pick an R so that the binomial CDF at R minus 1 is at least 1 minus alpha. Maybe 1 minus alpha is 0.95. Then the corresponding order statistic XR is the non-parametric upper tolerance limit. It's a very simple calculation. Also, the N minus R plus 1 order statistic is the corresponding lower tolerance limit. Very simple calculation. Okay, let us go back to this data. You have a sample of 208. I am going to illustrate the computation using just 50 of those 208 numbers. So here are 50 numbers from the data. So we need to order this from the smallest to the largest. There it is, because what we need is the order statistic. Now we will pick P to be 0.9, 1 minus alpha to be 0.95. So I will look at binomial NP. N is 50 and P is 0.9. is at least 0.95. If I look at the binomial table or go online and do the calculation, you will see that at 47, the binomial CDF is 0.8882. At 48, it is 9662. So if I want it to be more than 0.95, my R minus 1 should be 48. So R should be 49. So the non-parametric upper tolerance limit is the 49th order statistic, and that is 1742.4. Remember, I have 50 numbers. So 1742.4 is the non-parametric upper tolerance limit. The non-parametric tolerance limits are typically conservative because of the discreteness. Remember, I'm not getting 0.95 exactly, right? You cannot get 0.95 exactly under the binomial. So the coverage or the confidence, the actual confidence level will be more than the 0.95. So that is what is meant by being conservative. Okay. Two-sided interval. Actually quite simple. Now I want the Sth and Tth order statistics to form a two-sided tolerance interval. Again, you take Y to be binomial, R same as before. Now you simply write R as T minus S. Any T and any S, so that T minus S is R. Then the Sth order statistic and the Tth will be a two-sided tolerance interval. You see, it is not unique. Any T and S satisfying this requirement will provide a two-sided tolerance interval. It is not unique. What some people do is you take T to be N minus S plus 1 and then choose XS and N minus S plus 1 as the two-sided tolerance interval. This is a standard practice. It doesn't make it unique. Now, there's another issue here. The non-parametric tolerance limit may not exist unless you have a minimum sample size. And here is the sample size requirement for a one-sided limit, lower or upper. The sample size should be greater than or equal to the natural logarithm of alpha. Remember, 1 minus alpha is 0.95, so alpha is 0.05, and P is 0.9. Then this ratio, N should exceed that in order that the upper or lower tolerance limit will exist. For the two-sided interval to exist, N must satisfy this particular equation here. So the left-hand side should be at least 1 minus alpha, maybe 1 minus alpha is 0.95. So the minimum sample sizes, I have listed it here for both the one-sided and two-sided. For example, if P is 0.9, 1 minus alpha is 0.95, the minimum sample size is 29 for a one-sided limit to exist and 46 for the two-sided tolerance interval to exist. Of course, if you want P and 1 minus alpha to be very big, the sample size requirement could drastically go up. Okay. Let me give you one more example. This is taken from this book on laboratory medicine. So that is one of the field where this type of thing has a lot of applications. So this is data on this liver enzyme ALT. I will come back to this data a little later also. This is taken on a sample of 596 healthy male medical students. I have listed a few of the observations here. This is all data taken from this book. Sample size is 596. We will compute what is called a non-parametric reference interval. And namely, I want to compute an interval so that the content is 0.95. So 95% or more of the people will have their ALT levels within that interval with confidence level 0.95. So you look at binomial NP, N is 596, P is 0.95. And then if you look at the binomial CDF at 574, it is slightly below 0.95. At 575, it is slightly more than 0.95. So R minus 1 is 575, R is 576. You choose S to be 10, T to be 586, so that T minus S is 576. Then the two-sided interval consists of the 10th and 586th order statistics, namely the interval 8 to 68. This will be a non-parametric reference interval for the ALT values. Okay. It is a quick summary of what we have discussed in part 2. So we first discussed the computation of tolerance interval under the gamma using that cube root normal approximation. Then we went into the discussion of order statistics and their properties and discussed the calculation of non-parametric tolerance limit for any continuous distribution. And we pointed out the sample size requirements and we illustrated everything using several examples. I'll spend a little bit more time on part 3.
I have a question that I wasn't going to be able to type that fast. I'm just curious if you subsampled from your 208 values, you based it on a sample of 50. I'm wondering if you did that many times to see how many times your complete sample of 208 fell within your 95% confidence.
Okay, I follow your question. Let me go back there. I picked the 50 just for illustration. So the tolerance limit should be computed using the entire 208 observations. I wanted to show you some actual data because typing up all 208, it will take a lot of space and probably just a bunch of numbers. So I used 50 just for illustration. You are computing only one limit based on the entire data consisting of the sample of 208 observations.
I was just curious because you could do that many times with your.
I know. I follow your question. But then the thing is, why would you want to do that?
To check because this is non-parametric,
yes,
the 50 samples that you take could be skewed. And so you would get a sense of how accurate this non-parametric procedure is.
Well, the non-parametric procedure is accurate because it doesn't matter whether the distribution is symmetric or skewed as long as it is continuous. Because the theory behind the calculation, the properties of the order statistics, it guarantees that the limit will meet whatever requirement we want in terms of the content and the confidence level. That's guaranteed.
Got it. Thank you.
Yeah. Okay, you're welcome. Yeah. Anything else? Any other questions? Okay. So I'll first spend a little bit of time on the calculation of tolerance limits. So far we looked only at continuous distributions, normal, log normal, gamma, and non-parametric. We will look at now binary data, discrete data, assuming the logistic regression model, basically the binomial distribution, where the binomial probability P has the logistic structure. And we'll also look at some multivariate tolerance regions, ellipsoidal and rectangular, under the multivariate normal distribution only. Okay. You can also do multivariate non-parametric. We will not get into that today. Okay, many of these, I come to this based on various applications. So this was, we had a student from the Aberdeen Proving Ground, a doctoral student. He brought this problem to me. So this is of interest to the Army. Basically, what they are trying to do is they are trying to test the body armor, like the bulletproof vest, so to speak, regarding their how resistant are they to if some projectile or bullet hit it, are they safe? So what they do to increase the safety, they will insert an armor plate into the armor vest, right? You have the bulletproof vest, and into the vest you insert a plate in order to have extra protection. And then they test it out. They test out, having these plates, how effective is it in preventing, let us say, a bullet or some projectile penetrating. So basically when they test it, you can imagine the data will be, if a bullet penetrated, a bullet could either penetrate or not. So it is binary data. It is binary data, right? 0 or 1. No penetration or penetration. And you have to analyze that and see if the armor plate is effective in protecting these people. Now, the performance of this plate depends on a number of covariates. The size of the plate, the material used, and a very important covariate is the velocity of the bullet. right? If the bullet is coming to you at a very high velocity, probably the chances of it penetrating is much higher. So the velocity is a very important covariate. We will look at some data analysis also, the data I got from the Army.
Oh, Dr. Mathew, we have a quick question in the chat.
Yeah.
The non-parametric method is conservative. Does
Right.
that mean if you're calculating an upper limit that it will tend to be lower than it should?
No, it will be larger than it should.
Okay, thank you.
Yeah, conservative means when you compute, it will be larger than what it ought to be. Right? Okay, let me clarify that. Let me go back. Okay, let's look at this example here where we use that. In fact, I can go back to that sample size 50. Yeah, here you go. See, the coverage I want or my confidence level is 0.95. But I am actually getting almost 0.7, 0.9662. So when you have a larger coverage or a larger confidence, that will make the limit larger. So that is what is meant by conservative. So I'm not getting, I mean, there's no way you can get a limit that is exactly equal to 0.95 here. I mean, the probability or the coverage to be 0.95. So the non-parametric method tends to be conservative. Unless, of course, when the sample size is very large, that level of conservatism will decrease. Okay. So this is the problem we are addressing. So we have binary data, whether a bullet penetrated the plate or not. And that is what we are going to analyze. And the probability of penetration will be modeled using logistic regression that takes into account all these covariates here. So this is what I just said. The probability of penetration, we model it using logistic regression. And the Army wanted an upper tolerance limit for the proportion of penetrations among a specified number of tests. Let us say I'm testing the plate by firing at it 50 times. And what is the proportion of times it penetrated? Now, they do one more thing. While testing, they also insert some backing material. This is made out of clay. You mount that on the armor plate. Okay, let me explain that using this picture. So here is a picture. So the dark thing on the left, right here, this is the plate that is inserted. The next one in the middle, that is the body armor. This is the bulletproof vest. You insert this plate, armor plate. Then there is some clay backing material mounted on it before you test it. There you go. And here are various scenarios. So a bullet is hitting. This is so the plate, the armor plate, this is partial penetration. It did not penetrate through. So it is safe because you have the bulletproof vest here. Then the second and the third, it penetrated the plate, but it did not penetrate through the bulletproof vest. Then the panel on the right, these three represents, this is of course the dangerous situation. It penetrated both the armor plate and the bulletproof vest. This is complete penetration, which is obviously something we want to avoid. Okay, so this is a picture representing what we are talking about. Now, there are two observations obtained after a shot is fired. One is their penetration. So that is the binary data we are going to look at right now. Then, in case of no penetration, you collect data on what is called a back face deformation or BFD, which is an indentation on the clay backing material. Let's go back. So this thing on the right is the clay backing material. So because of the force of the bullet, even if it didn't penetrate, there could be an indentation here. So some type of the depth showing up, right? It will be pushed back, so to speak. And the amount by which it is pushed back will be measured in millimeters, and that is referred to as BFD or back face deformation. The data on the BFD is continuous, and typically it follows the follows the normal distribution. So we know how to handle that. It is a continuous variable measured in millimeters. So we are going to concentrate on the binary data, namely whether there was a penetration or not. So you collect data by doing N test. and notice each time whether there was a penetration or not. We also collect data on the BFD, which we will not look at right now because BFD is continuous. We know how to handle continuous observations. We have already discussed it. So here are some of the manuals and documents that will list what I just told you. And that picture I got from one of these documents, picture I showed you. I just copied it from the online document. One of the important documents is this one, National Institute of Justice Standards, 2008. They do require a tolerance interval to be calculated. Now the BFD is normal, so we know how to handle that. We will compute an upper tolerance limit using the normal distribution formula. And they want to verify if that upper limit is below 44 millimeters. So that is where their threshold. And due to some reason, they want content P to be 0.8. So I don't know why. Their requirement is the content is 0.8, the confidence level is 0.95. Okay, so this is under the normal. We discussed it already. Now let us see how we can handle the proportion of penetrations. So we'll define y equal to 1 in the case of penetration, otherwise 0. So binary data. And we write x as the covariates. Remember the covariates? We had size of the plate. This will be actually small, medium, and large. Three discrete, three possibilities, material used, and the velocity of the projectile. There is one more covariate we will discuss. Right. And the probability of penetration, we model it using logistic regression. So right here, it depends on the covariates through the logistic regression functions. And that's what they recommend, by the way. None of this is assumed. This is what is mentioned in this standards document. So I collected data after doing n test, and each yi is 1 or 0. And this is obtained for various covariate vectors. Now we look at m future responses for a fixed m, let's say 50. Denote that data by y n plus 1, etc., y n plus m. And suppose they correspond to a fixed covariate vector x naught. Then the number of penetrations will be the sum of these quantities, because this is either 0 or 1. 1 will correspond to penetration. So add them up, call that W. The distribution will depend on x naught, the covariate. So W will be binomial with m, because m future responses, and the probability of penetration will be pi x naught. So here is pi x, the logistic. So pi x naught is the probability of penetration as a function of the fixed covariate vector x naught. So the proportion of penetrations is W over m. So we want an upper tolerance limit for this quantity, W over m. So this is our problem. Now, what we will do is we will compute an upper tolerance limit for Wx naught and call that Ux naught, and then just divide it with m to get the upper limit for the proportion of penetrations. Now for the binomial is actually a fairly simple situation. Of course, we have the logistic function here, because to get an upper tolerance limit for the binomial, you can get it based on an upper confidence limit for the probability, binomial probability, in this case, pi x naught. I will not go through the derivation. The important thing was, how do you get an upper confidence limit? Okay, let me go back. Here is the parameter for which I want an upper confidence limit at a fixed covariate vector x. So I'm not looking for an upper confidence limit for the unknown parameters in the logistic function. I want an upper confidence limit for the entire function itself. You can do that based on likelihood-based procedures and their modifications. And once you compute an upper confidence limit for pi x naught, then you can get the required upper tolerance limit. And that's what we did. And this first author here, Zimmer, he used to work at the Aberdeen Proving Ground. He was one of my PhD students. And the problem was brought to me by him. And we solved it based on a likelihood-based method and published it. Okay, let's see how this will apply to the Army data. Now, the data they provided us consisted of 447 shots taken at various velocities, and they had a total of 149 plates. 52 of these were extra large, 46 extra small, and 41 medium. So this is the plate size, which is a discrete covariate for us. Okay. And on each plate, 3 shots were fired. So you have 149 times 3, 447 observations. Each observation is either 0 or 1. Then the shot number, namely, remember, 3 shots were fired. 1, 2, 3 in that order, let us say. And that was also included as a discrete covariate with 3 categories. Actually, that turned out to be quite important, as we will see. And the logistic model also included an interaction, some interaction terms. And the logistic was actually a very good fit for the data with these interaction terms and with these covariates. And of course, the velocity was a very important covariate here. So I'm going to show you. Remember, we are computing the upper tolerance limit at various fixed values or a fixed value of the covariate. We are going to use P equal to 0.95 and 1 minus alpha equal to 0.95. What happens if I test it 50 times? If a plate is used, tested 50 times on a plate, what will be the upper tolerance limit on the number of penetrations or the proportion of penetrations? So I'm going to show you a plot. Okay, let's see what this is. The first one corresponds to shot 1. Remember, we are firing 3 shots. So this is the upper tolerance limit corresponding to shot 1 and various velocity values. And the triangle corresponds to the extra large. The circle is for the medium and the plus is for extra small. For shot 1, shot 2, and shot 3. Interestingly, for shot 1, there is hardly any difference among the extra large, medium, and extra small. The limits all coincide, upper tolerance limit. You notice that as the velocity goes up, the upper tolerance limit is going up. Remember, I'm firing it 50 times, which means with a larger velocity, more penetrations should be expected, which is how it is. More penetrations are expected when it is fired using a larger velocity. You see that happening everywhere. Something interesting is for shot 2 and shot 3, the extra large gave a larger upper tolerance limit compared to the medium and extra small. No difference among the medium and the extra small, but the extra large gave a larger upper tolerance limit due to some reason. So we pointed this to the army and they were surprised. And they said, we will look into it. And I was curious to know if there was an answer to that. And they told me it is classified. So I don't know why that is happening. But the data analysis revealed something that was not known until we showed them this particular plot. Okay. Yeah, so this is what I just said. For the second and third shots, the extra large plate size results in a larger upper tolerance limit compared to the other 2 plate sizes at every fixed velocity value due to some reason, which I don't know. Okay, let me use this example. I used part of this example, creatinine, the creatinine data early on. The actual data is of dimension 3. So this is to assess kidney function using the amount of the urea, uric acid, and creatinine in the blood. And the data is available on 284 healthy subjects. So if I compute, suppose I compute a appropriate tolerance region, so to speak, based on this data. This is taken from healthy subjects, 284 healthy subjects. So if another individual comes to me and if the data on the urea, uric acid, and creatinine, if it falls outside the tolerance region, then maybe that is an indication of abnormal kidney function. A measurement falling outside the region is indicative of abnormal kidney function. So the region will be used for the purpose of diagnosis. So this is what earlier we called a reference interval. Now we will call it a reference region. So we'll write as X, X1, X2, X3. So this is the dimension 3 data on the urea, uric acid, and creatinine. We'll proceed under multivariate normality assumption, which is actually holding for this data. Of course, the multivariate normality doesn't always hold. Then we may have to look for multivariate non-parametric tolerance regions, something we will not discuss. So let X bar and S denote the sample mean and sample covariance metrics. Here they are from the data. And we are going to take P and 1 minus alpha, both equal to 0.95. Now, obviously, instead of computing a multivariate tolerance region, we can compute separate univariate tolerance intervals. Then the problem is that doesn't take into account the possible correlations among these three quantities. As we can see, the correlations are not that small, 0.54, 0.39, 0.22. This is the correlation matrix computed from the sample. So clearly, if these things are correlated, you want a region that will take into account the correlation. Okay, we'll first consider an ellipsoidal region. So here is the ellipsoidal region centered at the sample mean vector. And the shape is decided by the sample covariance matrix S, shape of the ellipse. And K is the tolerance factor to be determined. How do you compute K? Well, I want my content to be 0.95, confidence level to be 0.95 as well. You can theoretically show that the K will not depend on any unknown parameter. K will depend on the sample size, then the content P, and the confidence level 1 minus alpha. And for tabulating the value of K. So this is pretty easy to do. And you have the factor K available in tables. And once you have a problem, you can easily look up, get the factor and apply it. That R package also, you can get the factor K by using that from that R package as well. So I mentioned that early on. So here is the computation done for the example because we know what the sample mean is. We know the sample covariance matrix. And we have N. So with the P and 1 minus alpha equal to 0.95, the factor is 8.68. So this is the ellipsoidal tolerance region. Ellipsoidal tolerance region. Okay. Now going back to the example. So this comes under what is called a laboratory medicine. In fact, you can see the book says laboratory medicine here. Now this region, ellipsoidal, the laboratory medicine people are very hesitant to use it. Okay, let us see why. This is our region. Okay. Let's look at the univariate tolerance intervals for each of these quantities, ignoring the correlations. I compute separate intervals. So here is the interval for the urea, uric acid, and creatinine. And here is the sample mean vector. Okay, I'm going to look at two vectors, measurements on the urea, uric acid, and creatinine. In the first vector, the uric acid is 500, way beyond the sample mean. So the uric acid seems to be abnormal. In the second vector, the urea level is 8.86, way beyond the 5.1. So that seems to be abnormal. In fact, the 8.86 is way beyond the upper tolerance limit for the urea. So I have two vectors. In one vector, the first one, only the uric acid level appears to be abnormal. The other two are okay. In the second vector, the first component, the urea, appears to be abnormal. However, they both will produce for the value 14.74 for this quadratic form, x minus x bar transpose S inverse x minus x bar, which means both these vectors are outside the tolerance region. Both of them are outside the tolerance region because it simplifies to 14.74 beyond the factor 8.68. However, the two vectors are very different. In the first one, it is the uric acid that is abnormally high. In the second one, it is the urea. So what I'm trying to say is an ellipsoidal region cannot distinguish which component is outside the limit or which component is too high or too low. And this is one of the drawbacks of the ellipsoidal region. And hence, the laboratory medicine people are very critical of ellipsoidal tolerance regions or ellipsoidal reference region, as they call it, for diagnostic purposes. So I have put that here. An ellipsoidal tolerance region may not be appropriate to be used as a reference region for diagnostic purposes. Okay. Now, here is a very important application. It is referred to as hepatotoxicity. This is basically any drug can cause injury to the liver and cause liver damage. And hepatotoxicity means that drug-induced damage to the liver. And you measure that, assess that using elevated levels of this liver enzyme, ALT, we saw this earlier, and also elevated levels of serum bilirubin. You can see the FDA document on this. And the FDA document says drug-induced liver injury has been the most frequent single cause of safety-related drug marketing, withdrawal, etc. So I have the FDA document here. Okay, how do we assess hepatotoxicity? What we do is you compute an upper reference limit for ALT and an upper reference limit for the serum bilirubin. Any ALT level beyond 3 times the upper reference limit and 2 times the upper reference limits for the second thing, that is indicative of hepatotoxicity. So the conclusion is based on individual upper reference limits. This is referred as Hayes law, known after the person who first came up with this procedure to diagnose hepatotoxicity. One of the criticisms of this is that when you compute these reference limits, the correlation between the ALT and the serum bilirubin is ignored. It is not taken into consideration. So one of the prominent researchers in hepatotoxicity is Trost. He knows that since the cross correlations are not taken into account, existing multivariate reference limits are unscientific. And obviously, regulatory agency like the FDA rely heavily on this in order to assess hepatotoxicity. Okay, now ellipsoidal region is easy to construct, but the ellipsoidal region cannot answer the question concerning hepatotoxicity because it is just a region, right? It doesn't give you any information on the individual components of the vector. So this is pointed out in this book on laboratory medicine by Strike. It says that basically one large number could be kind of compensated for by another small number so that the entire vector could be inside the region, right? That can happen. So this is why they say that this is an issue when you want to go for a multivariate region like this. And secondly, the hepatotoxicity, you basically want upper limits. It is not an interval, not a region. We want upper limits. So basically, we want upper limits that take into account the correlations. In fact, you can have applications where on some components, you want an upper limit. On some components, we want a two-sided interval. That can also happen. And a region, ellipsoidal region, cannot do that. So basically, what we need is a rectangular region. So we need a rectangular region that will, for each component, taking into account the cross correlations. So I will not go into the computation of the rectangular region. It takes some time to explain, but we developed that in this paper, just published paper, how to compute multivariate rectangular tolerance regions that take into account the cross correlations, and we applied it to various laboratory medicine problems. Okay, if I go to this example, we have the sample mean vector, samples covariance matrix. And what we have done, we have computed separate two-sided intervals for each component. It's a rectangular region. We also looked at an upper limit for the urea and a two-sided interval for the other two components. So this is possible with the methodology that we developed. And so final comments. So the multivariate region, this is very, very important in laboratory medicine. And so they always talk about the need for such regions, but they hesitate to use ellipsoidal regions. And I explained why that is so. Unfortunately, they also recommend a prediction region, 95% prediction region. That means no mention of any content. This is clearly inappropriate. Some of them do recommend that. Well, that concludes what I want to share with you today. Any questions or comments, let me know.
I have a question if you have time, Dr. Mathew.
Yes, I have time. Go ahead.
Your very first example with the log normal data, only 15 data points, and you showed the tolerance limit was around 7 and the EPA limit was around 3.
Right.
I'm thinking there are two reasons that the tolerance limit will be high. One is that the 90th percentile is a high number, but also there's the sampling variability is substantial because there's only 15 data points. So I'm wondering if by increasing the sample size, you might be able to lower that tolerance.
Right. Yeah, good point. You are absolutely right. By increasing the sample size, you can lower the tolerance limit. That is absolutely right. The thing is that with such data, one of the things I hear, in fact, I have looked at data with sample size only 8. One of the things that I hear is that some of this data collection, it is expensive. So they don't want to collect a lot of data. And the price you pay is this, the observation you made is absolutely correct. So the price you pay with not having enough data is basically what you noticed with that data analysis. You are right. Especially some of the pollution data and so on that the EPA collects, and some of the, it's apparently it's very expensive to process a sample and eventually get the observation.
Thank you. And could I also comment on the groundwater example? I had asked a question earlier about the way the data were collected. I'm wondering, though, that if there's a point source leak under that landfill, it would create a alkalinity gradient, essentially.
Right.
And wouldn't necessarily be able to treat the data as random samples, putting a gamma beam.
Right.
So I would recommend graphing the data by location before doing the analysis that you showed.
You could very well be right. Some of this data, assuming them to be random sample independent, could be problematic. Now, what is going on there from the engineering perspective, I don't know. In the book, they treated it as a random sample. So I used it for illustration purposes, but that could be problematic, yes. So I just followed what they treated it as a random sample. They did do the necessary diagnostics for the gamma. The gamma part is fine. They treated it as a random sample. So we just followed that. That's all. That could be problematic. You are right again.
Thank you.
You're welcome.
All right, thank you, Dr. Mathew. I really appreciate you taking time out of your day to do this webinar for us.
Thank you, Elise. Thank you, Joe, for arranging this and having me, speak at your webinar. And if you want to follow up with any questions, feel free to email me as well.
If you're interested in reaching out to Dr. Mathew, as he said, you can reach him here at his email address, matthew@umbc.edu. And we have a webinar lined up for this December with Dr. Derek Tucker from Sandia National Laboratories. The link to register for this webinar is on the SDNS website. I hope to see you at JSM or at one of our upcoming webinars.